Welcome to Tolleson Physics. So now what we're going to do is we're going to apply everything that we've learned about energy to an interesting situation. And so we can use certain things to predict other things. So the example that I'm going to do for you today is, let's consider a Pinewood Derby race. Those little wooden cars that go down a track. So a typical Pinewood Derby track is 4 feet tall, which is about 1.2 meters. We can actually predict how fast the car is going to be going at the bottom, at least the maximum speed, assuming you can get rid of all the friction. And that's one of the hard things about building Pinewood Derby cars, is how do you get rid of all that friction, especially in the axles. There's a little bit of air friction as well, known as drag. But this would be the fastest it could possibly go just based upon the height. Now, the really cool thing about using energy is I don't need to calculate the forces. It doesn't matter if this is a curved track, a flat track, or anything like that. The only thing that matters is the change in height. So here's an LOL diagram. So what we're going to look at is we're going to look at the Pinewood Derby car, and then we're going to need the gravity of all of Earth. So at the top of the track, it's not moving until you release all the cars. So there is no kinetic energy, there's just gravitational potential energy. Now, I didn't write the other ones because there's no springs, and we're going to do this without any friction. So all of this gets transferred to kinetic energy. So, well, what do we need to think about? We actually need to think about what conservation of energy actually means. So conservation of energy really means that all of the energy that happens beforehand, and that's this over here, plus you could do some work. Like, so if energy was transferred from outside the system, that would be doing work on the system. You can also pull work away, like in the case of friction. And when you add those up, it'll equal the final amount of energy. So in this particular case, what do we have? All of our initial energy is stored at the top of the hill. So that's gravitational potential energy. And all of the energy that we're concerned with is contained in the system. So I'll write a 0 just so you absolutely positively know there's no work being done on the system. And then at the bottom of the hill, all the gravitational potential energy has been converted to kinetic energy. And so now that I've done that, now we're going to think back to those equations that we had come up with earlier. So for gravitational potential energy, the equation for that is mass times the acceleration of Earth's gravity times the height. And kinetic energy is 1/2 the mass times the velocity squared. Now, if you notice, I didn't give you mass of the car. Now, in Pinewood Derby rules, there's very specific mass that you can have. You can only go above a certain mass, and there's reasons for that because there's friction. We're assuming no friction here, so we're not going to account for that. But here's the interesting thing. Notice there's an M on this side, and there's an M on this side. And when you have the same thing on both sides, you can cancel them. So it actually turns out that mass doesn't matter, which should make sense, because when you drop two things, it doesn't matter how massive they are. They both drop at the same rate, especially in the absence of air. So there's actually, you can YouTube, do a quick YouTube search. You can find a video that shows a bowling ball and a feather being dropped at the same rate in a vacuum when there's no air drag. Okay, anyway, let's solve this. So GH equals, let me rewrite that. GH equals 1/2 V squared. Well, what I can predict at the bottom of the hill here is what's the fastest speed that Pinewood Derby car could be going. So let's solve for V. So I'm going to multiply both sides by 2. So V squared equals 2GH. And so V will equal the square root of 2GH. And so then what we're going to do is substitute those in to 10 meters per second squared. And what's the height? 1.2 meters. All right, and so then we'll take our calculator and we will see what we end up with. 2 times 10 times 1.2. Take the square root of that. And so it turns out the speed of a Pinewood Derby cart is 4.9 meters per second at the bottom of that hill. right? So that's the fastest it would go. And there's definitely friction in Pinewood Derby races, but now we can see what the fastest is and be able to calculate something interesting about the Pinewood Derby race. So we can apply this to many other situations. All right, the only way to learn physics is to do physics. So here's an additional problem based on the video that you can work on. So let's draw a LOL diagram and then come up with the answer to this question. So determine the maximum height a ball will travel if it is thrown at 30 meters per second and your arm is 1 meter above the ground. Like I said, start with an LOL diagram, hit pause, unpause when you have your LOL diagram finished, and then you can proceed to the next part. Okay, so first step was to draw that energy bar chart or LOL diagram. And so initially the ball has all kinetic energy. Now the thing that I decided to do is I decided that 1 meter above the ground actually is my height equals 0. You might have decided to put a little bit of gravitational potential energy in here, and that's okay. And so all of my energy, though, at the turnaround point is converted to gravitational potential energy because it's going from the up direction to the down direction, so at that instant in time, the velocity is 0. So now take this LOL diagram and finish solving the problem. Hit pause now and unpause when you're ready to see the answer. All right, so the next step is to take this energy bar chart and come up with an energy conservation equation. So initially I have all kinetic energy because I decided my arm is height equals 0, and then it's transferred to all gravitational potential energy. And then once I have that set up, my initial energy equals my final energy, then I can use the equations that we had come up with before. So kinetic energy is 1/2 mv squared, gravitational potential energy is mgh. Then you can follow how it's solved, and as you go through this solution process, my final height based upon where my arm was is 45 meters higher. So technically I need to add 1 meter if I want to know how high the ball is above the ground, because I started a meter above the ground. So 45 meters plus 1 meter equals 46 meters. So hopefully you tried that. Find other problems to work on and you will improve.